You know the deal. We're going to read some code. Today I'm looking at Pipewire. And I figured it makes sense to start in the examples so we get a feel for how Pipewire is used. Let's see. All right. I guess one thing, let's look at audio DSP filter. So this is in C as opposed to, say, C++ or C++. We're including some stuff I don't recognize, like SPA pod, SPA builder. I don't know if that's part of Pipewire. And then some just basic stuff like math and signal. And how small are we? About 160 lines. Let's see if we can find a super small one. These seem maybe to be about roughly the same number of lines of code. Okay, so audio DSP filter it is. Our data processing function is in general. Got a struct with a PW buffer, I guess Pipewire buffer, and some in thingy, in source, which is a Pipewire filter DQ buffer, which takes in as arguments a filter and an import, like a port you're going to listen on. And then out, we have another DQ buffer with an out port, and it's also taking a filter. And then we do stuff with the buffers, and then we call these PW filter Q buffers functions on the filter and the in and out ports. And for DSP ports, there's a shortcut to directly DQ. Get the data and requeue the buffer with PW filter get DSP buffer. All right. So we are at relatively high risk today for audio and video mishaps because once again, I just changed a lot of stuff about my setup. This should be hopefully a much better setup. For one, it's using Pipewire, whereas before I was using an old version of Linux Mint that the audio is really unstable and it caused me issues before. All right. So two things, I guess, two questions I have. One is, this is a little bit cumbersome, this syntax where you're doing one thing with an input and then the corresponding thing with the output, and then you do it again down here. This seems a little bit easy to forget one or the other, but that's really not so important. And then we've got this this on process function, which is going to take some user data. What is user data? I'm not sure, but it's a void star, so it could be basically anything. And then we've got a struct, which has this SPA thing, SPA IO position as a pointer. And SPA we recognize from up here. What is SPA? I still don't know. Maybe we can ask what it is. Let's see, where did SPA go? We have it under include. SPA IO position. The position information adds extra meaning to the raw clock times. Okay, so something about a clock and positions. It is set on all nodes, and the clock ID will contain the clock of the driving node in the graph. So Pipewire is building up a graph, and we'll see more of that in a little bit. And this position is telling us this position thing is set on all nodes, and the clock ID will contain the clock of the driving node in the graph. Okay, I guess, does each graph have a node? I'm not sure, we'll see. Then the position information contains one or more segments that convert the raw clock times to stream time. Okay, so we've got some raw clock. What kind of clock? I'm not sure. Maybe it's standard. I doubt it's like a monotonic, like Lamport style clock. Maybe it's just an ordinary system clock. And somehow we're going to convert raw clock times to stream time. What is this? What is stream time? I'm not sure. Maybe that's a version of the time that all the streams have to agree on. And then they are sorted based on their start times, and thus the order in which they will activate in the future. This makes it possible to look ahead in the scheduled segments and anticipate the changes in the timeline. Okay, something about clocks. And maybe we'll find out what's so interesting about clocks a little bit later. But right now I'm just trying to understand a little bit of the example. So we've got this struct IO position, which has the SPA IO clock and the SPA IO video size, an offset, which we're going to use to subtract from the clock position to get a running time, and a state. There's presumably some enum, and some number of segments, and a bunch of SPA IO segments. I guess that's n is the number of segments, and then these are the actually the segments. So what is SPA? Let me find out what SPA is. It's under include SPA. We have adapter control. Yeah, I'm not sure. Do we get a SPA README? No? All right. Well, let's go back to the example. And while we're pulling up the example, let's look up Pipewire. Let's add Linux, just so Bing doesn't think we're looking for something about RESTful SPAs. Simple Plugin API is an extensible API to implement all kinds of plugins. It is inspired by the many other plugin APIs, mostly LV2 and GStreamer. Okay, so we need more plugin APIs. And there are two parts, the header-only API with no external dependencies, and a set of support libraries or plugins for commonly used functionality. So we have some goals, no dependencies. I guess LV2 and GStreamer maybe have dependencies, very efficient in both space and time. Very configurable, consistent API, and extensible. The original user of SPA is Pipewire. So I don't know if this means that SPA is like competing in this space of like, if you're doing recording studio stuff, maybe in the future there will be SPA plugins, or maybe there are currently SPA plugins. So let's go back to the audio DSP filter. So we're going to take this SPA IO position thing, which is some position in the IO that's related to the SPA plugins. And we're going to set user data, have some in and out pointers to floats, which I'm going to guess we're going to think of as an array of floats. And we're going to set the number of samples to the clock duration from the position, from the SPA thing. Then we're going to log. And then we're going to call these in and out, the Pipewire filter get DSP buffer. I guess the user data has, among other things, the import and the output. And we're going to get a DSP buffer, and presumably n samples is going to tell us how large the size of the buffer is. We check that the buffer is not the in and the out that are returned by this Pipewire get DSP thing are not null. And then we just copy some stuff. We copy from in to out. Cool. And here's Pipewire filter events. And this is just what? This is a static const struct with this string, and dot process is equal to on underscore process. What does that mean? I'm not sure. We have do quit, which is just going to call Pipewire main loop quit on the data accessed on the loop accessed from the data. So user data, in addition to carrying the import and the output, is also going to have a reference to the loop. And it's called main loop. I don't know. I don't know if that's like the system loop or how to think of main in that context. But and then here's the main function. And we've got this SPA pod builder in it. I'm not sure what a pod is. I'm going to guess it's some grouping of plugins potentially. Kind of like a pod in Kubernetes is like a group of containers. And then we're going to call Pipewire init with the argc and argv passed in from into the main function. We're going to create a new loop. Make a main loop. If you already have another main loop, you can add the file descriptor of this Pipewire main loop to it. Okay, so you can make a loop, and that will give you some file descriptor, it sounds like. And if you already have a main loop, then you can attach things to it. And that's, I suppose, partially how we build up the graph. I don't know if it's a graph of loops or how we're thinking of it. And I also don't know if it's a, is it a DAG? Probably not. Is it a forest? I'm not sure. And then we do the PW loop add signal. And we're going to call get loop on the loop. I'm not sure what that means. Maybe loop is just some identifier and we have to call get loop to get the actual loop or something else with this. And we're also passing in this signal, SIGINT. And I guess, oh, sorry, we're calling PW loop add signal. So we're adding the signal saying that I guess if you receive SIGINT, then call do quit. And we're also passing in the data. I'm not sure exactly why, but I guess we need it. And then we're also adding the signal that if you get sig term, also quit. And then we're going to create a simple filter. The simple filter manages the core and remote objects for you if you don't need to deal with them. Pass your event and user data pointer as the last arguments. This will inform you about the filter state. The most important event you need to listen to is the process event, where you need to process the data. Okay, so you'll get some events, and if you get the process event, that tells you that you need to do some work, I guess. And so we call PW filter new simple. Pass in the loop. Again, calling the function PW main loop get to on the data.loop thingy. We're passing in on line 105 the string audio filter. I'm assuming this is the name. And then we're creating some PW properties. I'm not sure what these are, but these kind of look like, I was going to say key value pairs, but I guess they're not. We have what on the left looks like an enum, and then on the right, some sort of name. So or rather, yeah, I guess these are keys. So this media type is set to audio, media category is set to filter, and then media role is set to DSP. But these don't seem to be arbitrary key values. They seem to be, there's some constrained set of things you can set. And then we pass in a reference to filter events and data. Where did filter events come from? Somewhere. This seems to be the first appearance of it in here. And then we make an audio DSP input port. So I guess this is just creating a port. We call add port on the data.filter, which was assigned in the previous thing, assigned up here. And then we tell it that the direction is input, as I guess, as opposed to an output port. And then PW filter port flag map buffers. I don't know what that is. I guess we've got filters and ports, something about flags, and a map. And maybe this associates ports to actual buffers. I'm not sure. And then we pass the size of the port. And then we set some more properties. We say the format DSP is 32-bit float mono audio, and that the port name is input. Then we make an output port, and it's relatively similar. And then we have some parameters, setting params of 0 to the result of the function calling SPA process latency build. Process latency build. I'm not sure. And B, I don't remember where B came from, but we'll look it up maybe in a bit. B is probably some sort of buffer. It's this pod builder thing. We're going to pass in the pod builder, and we're going to set the parameter process latency to this thing, which seems to be, NS is presumably like nanoseconds, and it's going to be 10 times SPA nanosecond per microsecond. I guess this has units of time over time. And is that the right units for latency? I'm not sure. Then now we connect this filter. We ask that our process function is called in a real-time thread. So we call PW filter connect. We pass in the data.filter thing. We give it a flag, which is the real-time flag, and then the parameters, whatever 1 is, and y less than 0, I'm not sure. And if we're here, it looks like we have an error condition because it says we can't connect, and then we're going to return -1 if we can't connect. And if we're down here, we wait while we let things run. We just call PW loop run on the data loop, and then we destroy the filters and deinitialize. Okay, so that tells us a whole lot about how Pipewire is used and how they expect Pipewire to be used. I don't know. There's a bunch that I haven't seen yet. So let's take a look at some of that stuff. Um, and there's one variable or something that I wasn't sure where it came from. Was it filter events? Let's see if we can find filter events. Okay, this was declared on line 68. And it's this thing. I guess these are the events we're listening to. And this is probably telling us that, oops. Where is this comment here? The process event where you need to process the data. Okay. So I mentioned before that I didn't know what this syntax was referring to, but this is probably saying that this is like when you receive the event on process, and then on the right-hand side, it's like, what do you do with that? And what you do is you're going to call on process. What is on process? On process is this function we defined up here, which is going to do some logging, set input and output, and do mem copy. I guess just um, copy function from the input to the output, and otherwise act transparently. All right, cool. Now there are a few things that, so first of all, this user data struct seems to be super fundamental. Actually, it's not called user data, it's just called data. And which of these do we think is the actual data? I'm guessing it is in SPA. Is it in, not in examples? Not sure. What about the loop? See if we can find the definition of the loop thing. Data.loop. Look at this one. Okay. So now we're in, oh, whoa now. Now we're in source/pipewire /main -loop.c. And the PW main loop new function just calls return new loop, which I guess is just the internal version of the function. And what is the loop? Find out. Loop new. Okay, let's just go to the top. So we're just importing Pipewire stuff, none of this SPA stuff. And we've got do stop, which is going to take a loop, a Boolean. I guess the Boolean indicates whether it's async or not. A sequence, a seek, I'm guessing a sequence, some data, a size, and this user data thing. And we're going to set struct PW main loop this to user data. Okay. And then log, set this running to false. I guess stop the loop if it's running and then return 0. I guess that makes sense for do stop. All right, so here's loop new. We're creating this thing, which is the PW main loop, and that's the thing that we're going to return. And int res, maybe result, maybe resolution, probably not result because we're returning this. And then we're going to allocate the main loop thing. And if this is null, then I guess res is result because we're going to set it to the error number, and we're going to call goto, and then maybe possibly debug log. Again, check whether loop is null, in which case we'll call pw loop new on props, and props is a spa dict, probably spa dictionary that was passed in here. And if that succeeded, I guess we don't really ask whether it succeeded. We just say that it created it set to true. And then here, this is where we check whether it succeeded. If it's still null, we set result to negative of error number. Why negative? I don't know. And we call go to error free. as opposed to error cleanup. And then we set this loop to loop, which is hopefully at this point not null. And then we call spa hook list init on this listener list and return this. And the only thing that really creates a loop is this PW loop new, I guess. What makes it the main loop? I suppose because it's the one that is pointed to by this loop. I don't know. And why do we have these 3 checks for null? So if I guess if this is null, it's a failure of allocation, I suppose. If this fails, but I guess I don't see how this. So let's say that this. Oh, sorry. This is checking if this is null. I see. And then we're checking if loop is null, and loop was passed in. So if you pass in a null pointer, what it's going to do is create you a new loop. And if you tried to create a new loop, or you passed in a null pointer, I guess, and well, we're going to try to create a new loop. So if you pass in a null pointer and loop creation failed, then we get down here. And why is it negative error number? I don't know. Is that normal? I guess we're negating just whatever the current error number is. Not sure. And then spa. So let's take a look at PW loop new. This will probably be the thing that tells us about how loops are made. Create a new loop, returns a newly allocated loop. All right. And we've got this spa dict thing, which I don't think we've seen before, but it has some sorted items, which are flags and items, and spa dict items. And spa dict items are basically just key values. So maybe this is the sort of thing we saw before, where we're setting key value thingamajigs. All right. We've got an iFace, which I'm going to guess is interface, possibly like an audio interface. An impl is some implementation. Let's see. Direct impl. We've got a bunch of impls. Are they all different? Impls seem to have things like spa handles, spa nodes, spa log, node info, hook list. I guess hook list is probably some list of hooks that that can cause callbacks, and then callbacks are presumably the functions that are actually called. We've got the IO clock and the IO position and the in and out ports. So that's what I assume all impls look like until we see otherwise. And we've got a spa support. I'm not really sure what a support is. Extra supporting infrastructure passed to the init function of a factory. It can be extra information or interfaces such as logging. And we have a type of support item and a specific data for the item. So we're using a lot of like void star stuff to just pass in arbitrary doodads. And we call get support on 32. I guess 32 is here as the size of the support thingamajig. And we're going to create this impl thing and set this to impl this. We're going to check props, which is possibly passed in. Is this passed in? Yeah. The props is the dictionary of properties that's passed in by the caller. And if we have properties, we look up, I guess, the Pipewire key library name system. And we set that to the library. I guess let's look up what the possible name systems are. Maybe we'll do this in this other window. Key library name system. We get examples. I'm not sure. At any rate, it can be something. It's some lib. And then we set the implementation system handle to the result of trying to load the handle, calling pw load spa, passing in the lib that we got from the library system name and the spa name support system and the props object and the number of supports and the essentially vector or list of supports. And then if that failed, system handle will be null, and we'll say error stuff. And then we'll try to get the interface and set res to that. And we'll try to get that by the spa type interface system thing. And if that fails, we'll say we can't get the system interface. And we'll try to get props. We'll try to load the spa handle. I'm not sure exactly what a spa handle is. I'm going to guess it's a little bit like a file descriptor for spa stuff. Maybe we can find out what that is. Spa handle. It's got a lib, a factory name, a dictionary, and supports. Wait, no. That's just the function. Where's the struct? The spa handle. Def group spa handle plugin handle. Spa handle, spa plugin handle, and factory interfaces. Okay. So the spa handle has a version, and we've got some functions like essentially like a getter for the interface. But I thought we were looking at a struct, right? So we have a version and a getter. Get the interface provided by the handle. And that's really it, and clear. Okay. A bunch of this stuff, I don't know what the speed up of using C as opposed to C++ is. But a bunch of the code that we've seen so far seems to be, it could be made a lot more readable by using like C++ smart pointers, essentially. It looks like they're kind of like rolling their own smart pointers and whatnot. And I'm guessing that the reason they're doing that is speed. But I'm not positive. And I'm not sure, like, I don't know how you would, I guess, test whether the overhead of some, I'm not sure exactly what the C++ overhead you would be worried about is. Maybe the virtual function calls. I'm not sure how you would test whether that is slower or faster than doing things the way that they've coded them up without kind of implementing the whole thing in C++ and doing a test. At any rate, I don't think I was meaning to look at spa handle. What if I close this? I think this is what I was looking at. What's this? Okay, this is the loop new. We're still trying to create a loop. We do some stuff with supports. Spa support init. We check more prop stuff, or maybe we already did that. And we've got the spa handle get interface. We try to get the interface. I think we looked at that. We set this control to interface. I guess that's the interface is the one that's controlling it. And we set res to spa handle get interface, impl loop handle, spa type interface loop utils. I don't know what that means. Sounds like utilities. And the interface. We set this utils interface. We set this utils to iphase. And we return this. But where's the loop? What's actually doing looping? Are we using any loop libraries? We've got this spa support loop. We've got names, results, Pipewire loop. Let's look at Pipewire. Oh, that's what we're looking at. Loop that, see? Let's look at Pipewire loop. Pipewire loop object provides an implementation of the spa loop interfaces. It can be used to implement various event loops. And whatever this means, add to group PW loop. I guess that's a maybe annotation for the documentation. And this is a struct that has a spa system, a spa loop control, and spa loop utils, which is the util stuff we saw. And then a PW loop. Wait, what? This is a PW loop here. And we've got this function that returns a new loop. Let's take a look at spa loop. This is not spa. or rather it's the include. Let's see if we can find the source. Is it all just header only? I guess it is header only, right? Control? No? All right, support loop.h, sender support. Okay. And a spa loop is just a struct that has a spa interface in it. And a spa interface has a type and a version and some callbacks. And the callbacks, I'm going to guess, look mostly normal. So the callbacks contain the structure with functions and data passed to the functions. The structure should also contain a version field that is checked. So this is basically just a function. We've got like a standard function maybe. We've got the things that are like callable, and then we have data, which I believe is what it's telling us is those are just the arguments to the functions. And we've got the spa loop control. A spa source is a thing that has a bunch of spa loops, a spa source function, some data, a file descriptor, some masks, and a mask and an R mask. I don't know what R means here. And then private data for the loop implementer. So if you're implementing some version of the loop, you might need to have extra stuff, and you can just chuck that in there. We have spa loop methods. Register sources and work items to an event loop. And what can you do? You can add a source to the loop by giving it a spa source. Did we look at spa source? Yeah. So spa sources already have their own loops. So maybe this is building up the graph structure because now we're doing recursive stuff. You can update a source. You can update the source IO mask. I don't think we've seen what an IO mask is, but some sort of mask, I guess, that structures or configures the IO. You can remove it, and you can invoke a function in the context of this loop. And to invoke a function, you need an object. The function to invoke, the seek, whatever seek is, some data, which seems like it can be anything, size, whether to block, I guess, while invoking the loop, and some user data. And here's a version of spa loop a spa loop method. We have some control hooks, which they have a version executed right before waiting for events. It is typically used to release locks. So you can execute stuff before and you can execute stuff after. And they're mainly for locks. The hook before, here's an example of spa loop control hook before. You set the spa hook list star of L to L. L is passed in, I guess. I guess this is adding it to some list. We've got this struct spa hook H. I'm not sure what we're doing with it. And we're calling spa list for each reverse on H. L, getting the list from L, and link. I'm not sure where link is coming from. Or let's see. Yeah, and then we've got this spa callbacks call fast on before. So this is configuring it, I guess. This is the thing that's telling it to do looping to do before. So matching this. Why reverse? I don't know. And then link is presumably something that tells it to link stuff. Struct spa list link. It's a global of spa lists. It's just a linked list of spa stuff. Okay. So you've got this global linked list. And I guess what we're going to do is this is maybe going to reverse the list, then add it. Let's see what reverse does. Reverse on position head member is going to call list for each previous on position head member. I guess it's walking the previous. I think this is just reverse the list. Can I explain to you line 126? Oh, wait. This is a good question. Will this go over? Oh. For some reason, I can't move the chat over my VM right now. Yeah, maybe line 126 of which file? So I don't think it's that. Oh, yeah, no, I can't. This is what I'm trying to figure out here. I think spa list for each reverse is going to reverse iterate through the list. It's just a guess. And we're somehow adding the link, the thing that's passed in to the global of stuff, I think is what we're doing. And then this, I'm not sure that I understand. This line up here is not terminated. Right? Is that because I deleted something? That might be because I deleted something. Okay. And I forget what this does in a define. We've got this thing that's offset here. I think this is some trick, but let's ask ChatGPT what's going on. Oops, did I just erase it? What? What does this code do? All right. Here's what each part of the code does. This defines a macro named, takes a parameter L. This is and then the bracket, the parenthesis, curly brace stuff is the GNU C extension called statement expression. It allows multiple statements to be treated as a single expression. The entire block of code within the curly braces can be used as a single expression. Okay, that's straightforward. This declares a pointer to a structure of type spa hook list, and initializes it with L. This declares a pointer to the structure of type spa hook without initializing it. And then spa list for each reverse. This is a macro function for iterating over a linked list in reverse order, which we suspected. It iterates over each element in the linked list pointed to by the L list thing, assuming that this is defined elsewhere. And then spa callback call fast on this stuff with 4 arguments. It appears to be calling a callback function named before on each element of the linked list. Is that right? Maybe it is. We're passing the callback, the this struct thing, file loop control hooks before and 0. It appears to be calling name before on each of the. I don't think that's actually what it's doing, but we'll take a look at it. This accesses the CV member, which is probably callback. Struct spa loop control hooks specifies the type of the callback structure. Okay, before indicates a specific callback function to be called. I don't think that's right. I think that's supposed to be this. And 0 is an argument passed to the callback function. Okay. And then I'll ask, why is the last line indented? Is the last line the macro special? I apparently misspelled indented. Then what have I done? Indented. So it's not special. Indentation is primarily a matter of code style. Aligns the arguments of the functions. Okay, it's just aligning the arguments. All right. So you claim it doesn't seem to be aligning any arguments. I don't know. But let's look at this callback fast thing. So you're going to pass in callbacks, plural, a type, a method, a version. And it is going to call the callbacks, I guess. So we're going to cast the callbacks. So callbacks, right arrow funcs is going to be the actual functions, I assume. We're going to cast to the const type star. And then we're going to, I guess for each func, we're going to call the method on the callbacks data, which is they contain their arguments. And then whatever this is, these are like the VA, like variable args that are passed in, and we're going to return. I feel like the last line of a macro might be the return value. I mean, blah, blah, blah. For a macro to return a value, the macro itself has to be an expression. Your macro is a statement block. I'll ask, can a macro return a value? All right, maybe the last thing I'll ask ChatGPT is what is true doing here? It appears to be included to ensure that the entire macro. Oh, okay. Wait, where'd it go? Evaluates to a value, and specifically, it seems to always evaluate. Okay. Line seems to be included to ensure that the entire macro expression evaluates to a value. However, true by itself doesn't have any impact. The use of true in this context doesn't affect the functionality of the macro, but it might be included for syntactic reasons or to satisfy certain expectations in the code where this macro is used. All right. Fair enough. So that last line, line 126, does seem to be iterating over things in the list and calling functions on them. So that's fine. So I guess this line really just reverses. Although shouldn't there be a semicolon? I'm not sure. So I guess this reverses stuff and this calls stuff. Control hook before. And I guess after, we don't need a reverse because after means we're going to process in order. And I guess before means we're going to process in reverse order. All right. All of that's well and good. Here's, did we look at this? File loop control methods, control and event loop. This is for controlling the event loop. We can get the file descriptor. We can add a hook. We can enter a loop. We can leave a loop. We can perform one iteration of the loop. So I was thinking of loops as like a thing with a timer, a thing with a clock. But one iteration is this loop more like a for loop where we just have some like integer number of iterations. And we pass, at any rate, we pass control and a timeout, or I guess in case the iteration takes too long. The function will block up to a specified timeout, and then dispatch the file descriptors with activity. The number of dispatched file descriptors is returned, and then we can check the context of a loop. All right, and we've got some more control method stuff. So what does this mean? I still feel like I'm no closer to understanding what a loop is. Let me ask. I'm gonna start a new chat. Let's try Bard. Are you familiar with Pipewire. Oh, we get an image. Yeah, okay. So in the Pipewire code, what are SPA loops? Event loops that are used to manage the flow of data between different components of the Pipewire system. They are modules that can be loaded and unloaded at runtime. This makes it possible to customize the Pipewire system to meet the specific needs, blah, blah, blah. They are used for scheduling events to be executed at a specific time or in response to specific conditions, dispatching events, dispatch events to the appropriate components of the Pipewire system. This ensures that events are handled by the correct components, and managing resources. So we've seen them manage resources. We haven't so far really seen them schedule any events, or I would argue dispatch events. Um, does the do these loops use a particular event loop library? Okay, they use glib. Isn't glib just the so glib is a bundle of 3, formerly 5 low-level system libraries written in C, developed mainly by GNOME. I don't see any glib dependencies. Let's try Pipewire spa loop and see if we can find any write-up from them. Yeah. This is like a auto-generated API. Well, Pipewire loop tutorial. Thread loop. Threaded loop implementation is a special wrapper around the regular loop implementation. Yeah, I don't know. I don't know. So let's go back. And just for the moment, let's forget about loops. And let's just take a look at more of the code in source. We've got a daemon. We've got modules and Pipewire and tests and tools. Let's take a quick look at tests. There's not a lot of tests. We can text filter. And we've got some Meson build stuff. So they're using Meson as a build system. We've got things like core data loop. I think we looked at data loop, but let's maybe look at it again. Context, client cleanup, buffers. Maybe let's look at buffers and array. Introspect, a bunch of implementation stuff. I don't know if we want to look at any of them. Let's just look at the implementation header. We've seen loop and main loop, and they just kind of delegate to spa, right? There's some permission stuff. Maybe we'll look at the header and the C file protocol. I guess let's look at protocol. String might be important. Thread might be important. And I guess work queue might be important. I'm going to try to blast through these though. Let's start with protocol. Pipewire protocol manages protocols and their implementation. And we have a protocol client, which again has got a spa thing, a spa list, which is, given that it's named link, is probably supposed to be a linked list. And a PW protocol struct, which is the owner of the protocol, a core object, and some sort of connection, which is recursive because this is a protocol client inside of a protocol client. And as a SPA dictionary, some callback stuff, a file descriptor for the connection, I guess. Oh, these are functions, right? Yeah, okay. So you can connect. I guess you can steal a file file descriptor from something else, you can disconnect and destroy. And then we have a Pipewire protocol server, which has a linked list of SPA stuff, the protocol, a core again, and a client list. So the server is aware of its clients, and you can destroy it. And protocol Marshal is presumably going to take the bit level protocol and turn it into structs. And we have protocol implementations, but I want to see what the actual protocols are. Here's the actual protocol struct. We've got a context. I guess protocols have a context. I have a list of marshalers, a list of clients, list of servers, and event listeners, and an implementation. Can you find any let's see if we see any, can see any actual implementations. Here's an implementation, possibly, but not really. Simple new client. Let's see here. Yeah, I'm not sure. I'm not sure like what protocol it's implementing. How is the protocol defined? These are things that I'm not really seeing in any clear way, but that's okay. That's protocol.h. I'm going to assume protocol.c is not any more instructive in that sense. Here's pipewire.h, which should be maybe the main entry point. Got about 104 lines. We're including all the things. And this is maybe mainly for initialization. We have things like get application name, get program name, get support. We've seen support, SPA supports elsewhere. Load SPA handle and unload SPA handle. And some val grind stuff, I guess, for checking your, doing testing and debugging. And then we've got this init function. I guess let's take a look at Pipewire init. Initialize Pipewire. All right, so got some dict items. We're gonna mutex lock. We're using pthreads, and we're gonna lock some stuff, whatever the init lock is. I guess it's the thing that locks initialization. And okay, and then we're gonna call random init, I guess, to initialize maybe a random number generator. And then we're gonna lock the support lock. I guess supports have their own locks, and do some val grind stuff. DL close. I'm not sure what DL close is. We're closing some stuff, I guess, that might have been open from a previous run of Pipewire. We're going to initialize the SPA registry and I guess the plugins and the handles, rather. Pipewire log is default. I guess this is just logging stuff. We're checking if the logging is default somehow. At any rate, we're going to log init on line 634. And we're going to look at the CPU and I guess whether we run a VM and get some dict items, which we possibly populated before with the CPU and stuff. Add internationalization support, add an interface. And then unlock the initialization. And then deinitialize Pipewire is presumably similar. Okay, so that's Pipewire. Look at thread.h. I'm guessing this is not so fancy. We can create their threads, join threads, and since we're using pthread, right? I'm going to guess this just calls out the pthread. Oh, so defined as by as calling the SPA stuff. We have pthread here. This can be cast to a platform native thread like pthread on POSIX systems. So I guess you can use pthread, but maybe this is an abstraction that supports other possible threading utilities. So let's look at like join. SPA interface call res. SPA thread utils join. SPA thread utils create. Maybe let's look at create. We're going to create a null thread and call SPA interface call res on the interface with this SPA thread utils method res create 0. This is like I'm not sure how this is actually instantiated in real life. It seems like a lot of what we're seeing is kind of like wiring things up. Everything seems to flow through SPA. And then you would expect to see, I guess, some sort of final, like maybe SPA is something that gets implemented on a platform by platform basis. I don't know. Let's take a look at, but we'll try to dig into that, I guess, as we get to the end. So here's work queue. What do we have? We can create a new work queue. We can destroy a work queue. We can cancel, add stuff to it. Let's just look at creating a work queue. Did we see an actual struct? Okay, yeah. Okay, so a work queue is something that has a loop, a SPA source wake up. I'm not sure what SPA source is meaning, but maybe this is the thing that wakes up the queue. A list of work to do, a free list, a counter, and the number of things queued, I suppose. SPA list is just a generic linked list. And what is SPA source? Again, it's a thing with a loop and some functions and some masks. What is it actually doing though? Using loop.c. All right, what it's doing, I don't know. Maybe let's try here. If we do, let's look for wake up in GitHub. Maybe there's something wrong with my search that's not finding. But yeah, maybe for some reason my search isn't finding a bunch of stuff. Void wake up main. So that's different from just wake up. We have wake up func. Let's look at wake up func. This is just some setting implementation of data and flushing items. All right, I'm not sure. Okay. So that's work queue. I still don't really understand what's going on with that. So stream. Streams. Streams are used to exchange data with the Pipewire server. A stream is a wrapper around a proxy for a Pipewire client node with an adapter. This means that the stream will automatically do conversion to the type required by the server. Okay, so we have some automatic conversion. The wrapper around a proxy for a client with an adapter. So the client is presumably just a client. Maybe the adapter is the thing that's doing the conversion. Streams can be used to consume a stream from Pipewire as an input, produce a stream to Pipewire. You can connect the stream port to the specific port, blah, blah, blah. You can also implement a sink and a source. For more complicated nodes such as filters or ports with multiple inputs or outputs, you will need to use the Pipewire filter. All right. And we've got connection stuff. So this seems to be maybe the heart of it. We get a huge comment that's describing what streams are about, which is the repo is in general a little bit under commented. It doesn't tell you what a lot of things are doing. I'm getting a suggestion to take a look at thread loop. Did we look at thread loop? I thought we've seen thread loop, but let's just add it to our queue. All right, but back to streams. Whoa. Okay, so streams have a state, which is error, unconnected, connecting, or paused or streaming. And we have a buffer structure obtained from the DQ buffer, the deck buffer. I think it's pronounced DQ. The size of the structure can grow as more fields are added in the future. Okay, so we have a spa buffer, which is presumably just a fancy buffer. It's got a buffer with metadata, and we're keeping track of the amount of data and metadata. The buffer has the spa buffer and also user data attached to the buffer, a size, then requested. For playback streams, this field contains the suggested amount of data to provide. For audio streams, this will be the amount of samples required by the resampler. Okay. You can request how much data you want. This field is 0 and no suggestion is provided. All right. Then you've got some control over the stream. You can name the control. You have flags to I guess, configure the control. You have min and max values of what? I'm not sure. Of the stream. And an array of values. I guess maybe min and max of the array of values. And then the number of values and the max values that can be set on this control. And we get a time structure, a PW stream get time n to get an updated time snapshot of the stream. The time snapshot can give information about the time of the driver of the graph. The delay to the edge of the graph, and the internal queuing of the stream. I guess delay to the edge of the graph maybe means like latency of processing all the audio in the graph. The PW time ticks gives a monotonic increasing counter of the time in the graph driver. Okay, so we do have a monotonic clock. It can be used to generate a time to schedule samples as well as detect discontinuities in the timeline caused by X runs. So X runs are these like error conditions, and I guess they cause discontinuities in the timeline, like maybe like jump discontinuities. Do you have an official definition of X run? Buffer overflow. Okay, so it's, I guess, under the hood, just a buffer overflow. PW time delay is expressed as PW time rate, the time domain of the graph. This value and PW time ticks were captured as at PW time now and can be extrapolated to the current time like this. And then we've got some code. All right, so this is finally some timer stuff. Here's an overview of the different timing values. We've got some sort of stream time domain, a graph time domain, a queue, and a DQ. So as we queue stuff, there are some buffers, I guess. Then we have a converter, and that's in the, I guess, the stream time domain. And then in the graph time domain, we do graph stuff, graph latency. And then we get, maybe this is like just latency of graph operations. And then we get, I guess, into the kernel, which is the calling internal latency. And then the kernel is going to directly drive the speaker. This says, and then we have queued. This is queued stuff. This is buffered stuff. And then we have delay. And then PW time is a struct. We've got a rate, which is I guess a custom fraction type. The rate of ticks and delay. This is usually expressed in 1 over sample rate. We have ticks. The ticks at now. This is the monotonic clock, I guess. And then we have a delay to the device. I guess this is probably measured, right? This is the time it will take for the next output sample of the stream to be presented by the playback device. Or the time a sample traveled from the capture device. Delay includes the delay introduced by all filters on the path between the stream and the device. Delay is normally constant in a graph and can change when the topology of the graph or the quantum changes. This delay does not include delay caused by queued buffers. And then data queued in the streams. Some buffered stuff. and queued buffers and available buffers. Now, the next thing I want to know is delay computed empirically, or do they like pre-compute it with like known values? This maybe is interesting. No, we see lots of declaring of delays. Hold time, delay implementation. Wait, hang on. Maybe what I want is maybe I'm just going to yeah, I don't know. I don't really see anything setting a delay. I see lots of declarations of delays. Let's try GitHub again. Delay run. Here's audio convert. It's void. Delay convolve run. It doesn't seem to be setting delay. Do we have like delay equals anything anywhere? We set max delay. Here in loopback, we're setting delay equal to a fixed thing, which is spa minimum of the delay and some factor of the buffer size divided by 4. Here, I guess delay is being set to essentially an argument, it looks like. Here, delay is being set to something computed from the clock and the clock delay. Yeah, I don't know. So it seems like we're setting maybe here. Delay is info rate times request number. It seems like delay is something that's like a theoretical delay rather than actually measuring what the empirical delay is, which is seems like it'd be extra cool to have like an empirical measurement of the delay, but I'm not sure. Thank you, Henri. Henri says, I hope you upload this to the channel. Please don't stop the awesome work. I appreciate it. I will upload it to the channel. Unfortunately, I'm running out of time. I don't feel like I have a good sense of how Pipewire is doing things. I think so streams is really important. I think that if I were to do a second pass, I would focus a lot on streams and the timers. And if you look at, so what is this sort of thing trying to do? So if I don't know if you've like ever seen like an audio patch bay or a recording studio or whatever, but basically, you know things like this, where um, outputs of one thing need to be plugged into inputs of another, and um, uh, and this is the sort of thing that something like Pipewire is emulating to some extent. See if we can find a famous mixing board. Yeah, so here's an old school mixing board. And the way that these old mixing boards work, these controls here are called faders. These are just potentiometers that are linear potentiometers. And each one essentially, maybe like up to here, is a track that you can plug an instrument into. And then as you go down this strip, these are like other potentiometers that do things like pan to the left and right and set gain and equalize and whatnot. So like an old school mixing board is built up of these strips. And this kind of strip is maybe one stream or one stream-like thing, I think, in Pipewire. And then and you have a bunch of them together. They can be chained, like you have you can make the output of this thing go into the input of that, and that's going to give you a graph structure. And what Pipewire is doing is kind of efficiently modeling this sort of thing so that like if I'm recording audio, let's say on my computer, or I'm like recording a guitar while I'm also watching a movie, um, Pipewire or something in Linux needs to figure out like, okay, the movie audio needs to go to these headphones, but the headphones also need to hear the feedback from the guitar, and the input of the guitar needs to be recorded, but the movie shouldn't be recorded. So those sorts of things is what um, Pipewire is about. And just for fun, let's see if we can find a mixing board strip. Just so it doesn't strip doesn't give me something bad. See if we can just find a single strip. I think kind of like this. I think you can, buy. Here's just a single strip, and I think that in the old days you could manufacture like 4 strips and put them together, and that's what the early like 4-track mixing boards were up to. All right, so that's kind of just background. All right, and so each of those all this audio stuff has some notion of sampling. We're working in the digital world as opposed to the audio world. So there's some sampling going on uh, frequently around like 44K or like 48. Um, and so that means that there is some oscillator, which I'm assuming is part of what is going on with the clock. And then just in addition to all the oscillators, we need to be aware of which things come before which other things, which is another thing that you have to account for with clocks, I think. All right. So here's thread loop. The threaded loop implementation is a special wrapper around the regular PW loop implementation. The added feature in the threaded loop is that it spawns a new thread that runs the wrapped loop. Okay. So this is going to, this is another layer of abstraction over loop. I feel like I never really saw the concrete implementation of loop. So just in the interest of time, and because our vision of loop is already pretty abstract, I'm going to mostly ignore that. Here is the spa loop stuff, I think, which we already saw. Here's main loop, which we definitely already saw. Impl, I'm not sure what this is going to be. But we saw some impl stuff. Data loop, I'm not sure if we saw. Loop events, using PW data loop add listener to add a listener. And we can destroy the loop. We can create a new loop, add a listener, start, stop. But again, these should all just be like calling out the spa, right? Oh, no, this looks loopy. If loop is not running, yeah, okay, then we do some spa stuff. We set loop running to true, etc. Spa thread utils require real time. I guess this is for getting real time stuff. Okay, and then core, the core global object. So this is like maybe like a God object, a special singleton object that is used for internal pipeline protocol features. Connecting to a Pipewire instance returns one core object. The caller should then register event listeners. Okay, so you're going to get like a reference to the singleton, and you're going to add listeners to it. And this is presumably like the single mixing board that's going to control all of your stuff. And core info, we have an identifier for the global thingy, a random cookie for identifying this instance of Pipewire. I guess random so that if you have multiple machines, is this for like, I don't know if this is in case you're trying to run Pipewire twice on the same machine, or if you have a network. I'm not sure if Pipewire communicates over the network, or maybe it's for if you have like a VM or a container that are multiple containers that are running Pipewire. I'm not sure. And then we have a username, who started it, the host name that the core is running on, version and whatnot. And then we have a bunch of events like info, done, ping, remove ID, bound ID, add memory, remove memory, bound props, and event number. And then we have this core events thing. You can notify new core info. This event is emitted when first bound to the core or when the hello method is called. Okay, so this is like you joined some group and you're getting a hello message. You can say that you're done. It's emitted as a result of a sync method with the same sequence number. Seek, okay, so seek, I guess, is probably the sequence number. We've been seeing it before. I'm assuming it works more or less like it does in networking, that you just maybe these are messages that can possibly be lost, and so we number them so that we know when we've seen them. We can emit a ping event, et cetera, et cetera. Okay, so this seems to be mostly about communication. Buffers, we saw some of the buffer stuff. They're just arrays essentially, or buffers, but they keep track of things like metadata. And here's arrays. These might be proper arrays. We have the data, the size, allocated memory, and extend. So these are probably going to be so these are going to be like arrays that do the normal thing where every so often it's going to double its size to make sure that it has room for adding more stuff to the end. Okay. All right. So GST, this is probably GStreamer. Yeah. So this is GStreamer stuff. Is GStreamer the implementation that I've been looking for? GST Pipewire Core. Opaque data structure. So we've got some, whatever a gint is, I guess an int. It's some reference count for what? Maybe for the core object. And we've got a loop, which is a PW thread loop, PW context, PW core, and some SPA stuff. We get a loop. You get sync sources. All right, so this is GStreamer stuff. We haven't really looked at GStreamer, but maybe we can at least look quickly at the Wikipedia page. A pipeline-based multimedia framework that links together a wide variety of media processing systems to complete complex workflows. For example, you can build a system that reads files in one format, processes them, and exports them in another. I don't really know what GStreamer is used for. I used to see it, I feel like, a lot. Maybe it's just built into everything now, or maybe other things have is it related to FFmpeg at all? In addition, there is a GStreamer FFmpeg plugin. Yeah, I don't know. Okay, so GStreamer. That seems to be like an implementation of Pipewire using GStreamer, perhaps, or maybe the other way around. Maybe it's like Pipewire as a thing that is controlled by GStreamer. Here are examples which we looked at. The daemon, I don't think it's going to tell us too much. We have a jack config. That's for the jack audio daemon. Pipewire.c. This is relatively simple. Things like creating Pipewire contacts, properties, etc. And systemd, for what? I don't know. This is like Pulse, I'm going to guess, is Pipewire Pulse audio interoperability. And so what are we missing? We see SPA. Port monitor, utils, device, event. What's an event? Did we look at events? Device start, device object, device props. Control. And what else? We see Pipewire ALSA, Pipewire Jack, Pipewire video, maybe video for Linux? And then PO is the internationalization. All right. I still feel like I don't understand what the actual clock stuff is. We saw a little bit of it. Let's see if I can find it relatively quickly. Lots of loop stuff. I mean, I guess let's go back to SPA support loop. This is all SPA stuff, and we import pthread. And we can invoke a loop. Let's see what invoke loop does. Calls invoke loop in thread. You get something on a ring buffer. The ring buffer can only be written to and from one thread. We are in the same thread as the loop. Don't write into the ring buffer, but try to emit the callback right away after flushing. What function is this? This is loop invoke. So we have some sort of ring buffer. We check if impl thread is 0 or pthread is equal to. So I guess if the impl thread is the same as the current thread, then we call invoke in thread. Otherwise, we call spa ring buffer get write index on the impl buffer. And this is, I guess, the stuff that's filled. If we filled less than 0, or we filled the whole thing, then we warn that there's an X run. We return negative of epipe. Otherwise, I guess we have space left. And the available space is data size minus the filled space. And if the available is less than the size of, I guess, the thing that we're supposed to fill it with, the invoke item, then we say that we don't have enough room for it, and there's an X run. Wait, there's not an X run. We just say, I guess we can't do it. We return negative of epipe. And then we get the offset, which is whatever IDX is, but basically the size of the current data minus 1. L0 is the remaining size in ring buffer. This should always be larger than the invoke item. See below. I don't know why you need to see below, but that should be guaranteed by the stuff we saw before. But we're going to, the remaining size in buffer should be, I guess, where we're essentially going to write this thing. I don't know if we locked anything. I don't know if we have to worry about something else coming in and writing after we've done these checks. Okay. And then pointer off, maybe pointer offset, setting some stuff like the item function, item sequence, etc. And if L0 is bigger than or equal to item size, then they fit in the current buffer. And we're just going to write them, right? We set item data to be the SPA pointer offset, I guess, which we called before, right? SPA pointer off here. And if L0 is less than the size, then we have not enough space for the next invoke item. Fill up till the end so that the next item will be at the start. Okay. And if we're down here, then the item does not fit. Place the invoke item at the index and start the data at the start of the ring buffer. Place the invoke item at the index and start the data at the start of the ring buffer. So I guess we're at some index and we're just going to restart over at the beginning because we can't fit the item in. And if we're down here, there's something about stuff being suppressed. If available is less than item size. I forget how available is related to L0, but I guess more checking that we can fit stuff. And then if everything looks good, then I guess we just do mem copy. And get study learn up is saying, I think here clock used to store the timing reference when we have multiple audio. I'm not sure when you said that, but that's definitely one thing. One thing that they need to store. I guess I'm feeling a little bit like I'm not seeing as much of the clock as I expected. But at least now we're getting something that looks like a loop. We're getting this ring buffer stuff, and we're checking it for blocking, etc. Okay, so this is going to be loopy. We've got a ring buffer, so that makes sense. And we've got some events. Let's try looking for clock. System.c is promising. What is this? Pipewire plugins. So we have like a timer file descriptor and whatever clo exec, maybe clock exec, timer fd create with a clock ID. So here's some timer stuff, and here's some event stuff and some signal stuff. And what struct is this? This is SPA system methods. Okay, so SPA system methods is going to, I guess, specialize the SPA stuff for systems. Where can I find implementations? I don't know. Here's an impl system, and we're just calling these impl things. How about impl clock get time? I'm not sure. I guess we're getting them by using these like system libraries or whatever, right? I don't even know if Pipewire supports like Windows. So is Pipewire only on Linux? So maybe there's only really one system to consider. I think it maybe is only Linux, which would be hard to think how you would do it for multiple OSs. So I'm guessing that the reason I'm not seeing like some of the clock stuff is we're just delegating it really to the kernel. Did I want to find, so we saw the monotonic clock. There's something else that was, I feel like that was mildly interesting about clocks from the very beginning. And let me think for a second if I can remember what it is. We can at least look for, what is it, 44 audio sampling rate. 44.1. So 44 doesn't appear anywhere, at least not. Tag file doesn't count. What about kilohertz? We do have some kilohertz stuff. A lot of it's in the tags file. And modules. Maybe modules is where I want to be. So we do see some things that look like audio stuff. So we have 16 kilohertz, 32 kilohertz, PCM. I don't remember what PCM is, but it's something you see a lot with ALSA. AVB, audio video bitrate, maybe. And we have stream IDs. So maybe modules is the place to be. Is that where I am now? Yeah. Okay. We have things like jack tunnel, loop back, metadata. Okay. So I underestimated modules, but this maybe RTC is like real time. The RT modules can give real time priorities to processing threads. Yeah. So I think a lot of the work is in modules. A lot of the like pulse tunnel is presumably going to be tunneling to pulse audio. The pulse tunnel module provides a source or sink that tunnels all audio to a remote pulse audio connection. All right. I'm not going to dig in any further though, because we're about an hour and 31 minutes in. So that's all for me. That was Pipewire. It's cool. It's a little bit hard to understand the code on the first go round. We may, some of that may be just my lack of familiarity with the Linux audio system in general. But I also found the code to be not super commented. And there's this deep interconnect between all the pulse audio stuff really just delegates to SPA. And then there's a lot of stuff in SPA that's like, we're going to create kind of like a function calling convention, and it's not really clear where in some cases where the work actually ends up happening. Um, and I assume that the reason that it's structured that way is because Pipewire wants to be very flexible, and in practice, it ends up being, um, in my opinion, much better than what we had um, for audio on Linux. In terms of usability, I don't know how it ranks up if you're doing like professional audio, like if the latency is as low as just using pure jack or whatever. But anyway, that's Pipewire. Hope you enjoyed it, and thanks for watching.